right, so we want to take a look at this question here, and it says, two smooth vertical walls meet at right angles. The smooth sphere A with mass m is at rest on a smooth horizontal surface and is at a distance d from each wall. An identical smooth sphere B is moving on the horizontal surface with speed u at an angle theta with the line of centers when the spheres collide, as seen on the diagram. After the collision, the spheres take the same time to reach a wall. The coefficient of restitution between the spheres is a half. So on part A, find the value of tan theta. All right. Okay, so to answer this question, we're going to consider this to be before collision, and we also need an after collision. So this is before and this is after. And for after collision, we'll have the same spheres. Okay, so here are the two spheres. All right. And we are going to have the line of centers passing through like this. And we are going to say, okay, for the components before collision, the component of u that is perpendicular to the line of centers will be this one here. And I'm going to call that u sine theta. Then the component that is in the line of centers is u cos theta. Then for particle A, we're going to have zero components for it before collision because we have been told that the sphere A is at rest on a smooth horizontal surface, okay? So it starts out at rest. Now, after collision, all right, after collision, for sphere B, this is still sphere B, the component of B that is perpendicular to the line of centers is not going to change. So it is still u sine theta. The component that is in the line of centers, I'm going to call that VB. Then for the other particle, okay, this is particle A, we're going to say here that we can deduce that it is going to move to the right after collision, okay, towards the wall. Remember, there's a vertical wall here, and the distance to the vertical wall, this distance here, they say it is D. So this component, I'm going to call it VA. All right. So applying the principle of conservation of momentum, we're going to say that in the line of centers, the momentum before collision is equal to the momentum after collision. All right. So the momentum before collision in the line of centers would be mass times the speed, which is in the line of centers. So it's m of u cos theta, basically. So mu cos theta. And that's for particle B. Particle A will be at rest. So there's zero momentum for it before collision. And then this is equal to the momentum after collision. The momentum for B will be mass times VB. So we have m VB plus for A, that's going to be, this is particle A, remember, that's going to be m VA. So m VA. All right. So we can divide everything by m so that we can have VA plus VB is equal to u cos theta. Okay. So I've just rearranged after dividing everything by m. I now have this. Okay. And let's call this equation 1 as we are most likely to need it a little later. All right. Next, we want to apply Newton's law of restitution. Okay. So basically, we're going to say again in the line of centers, okay, or along the line of centers, okay, the relative speed of separation is equal to E times the relative speed of approach. So basically, Vs is equal to E of Va. Now, the relative speed of separation, okay, for this, we say Va minus Vb. All right. So that's what we're going to do here. That's Va minus Vb, and that's equal to E of the relative speed of approach. We say the speed of B minus the speed of A, but the speed of A is 0. So in the line of centers, the speed of A is just U cos theta. All right. So it's E of U cos theta. Let's call this equation 2. And what I'm going to do here with the two equations, I'm going to add them up. So equation 1 plus equation 2, this will help eliminate VB. All right. So we'll be having then 2VA is equal to U cos theta plus EU cos theta. All right. We can also write it as 2VA is equal to 1 plus E of U cos theta. So that's after factoring out U cos theta. All right. Now in the question, there's also something very important that they have told us. Okay. There's a statement here which says, after the collision, the spheres take the same time to reach a wall. Okay. The spheres take the same time to reach a wall. All right. So let us consider that fact because it's a very important one. All right. So if the two spheres take the same time to reach the wall, it means that the time taken by the component, this component of B to hit the wall, in this case, it will be the horizontal wall, is the same time taken by A to reach the vertical wall, the other wall. All right. And what that automatically means is that since they're taking the same time and they're traveling the same distance, because again, the distance to this wall here is D, so they're taking the same time and the same distance, it automatically means that the speed of A as it approaches the wall is the same as the speed U sine theta as it goes towards the wall. So essentially, what I'm saying here is um, we should take note that the particles take the same time to approach the perpendicular walls, and they travel the same distance. So because of that, it means that the speeds as they go towards those walls should be the same. So essentially, the speed of A approaching the wall is VA. So we're saying that VA is equal to the component towards the wall of B, which is U sine theta. So it's U sine of theta. So that's the conclusion we get. All right. So if this equation we got from combining is equation 3, and this thing we've gotten is equation 4, we can actually substitute, therefore, substituting 4 into 3, and this would mean that we'll be having, for VA, we use U sine theta, so 2U sine theta is equal to 1 plus E. We have been told that the coefficient of restitution, okay, between the spheres is a half. Okay, so where we say 1 plus E is 1 plus a half, and 1 plus a half is 3 over 2. So we essentially have 3 over 2 of U cos theta. All right. So we still have space. We no longer have enough space. So we are just going to say here, this is the same as if we multiply both sides by 2, we get 4 sine theta being equal to 3 cos theta. And if we divide both sides by 4 cos theta and this side by 4 cos theta, this will lead us to having on the left side tan theta, because the 4's will cancel and sine over cos is tan, and cos will cancel, so it's 3/4 we get on the right side. And that's the value of tan theta that they want us to find here. So I'll say here, that's the answer. All right, that's the answer. Let's move on to part B. Part B says, find the percentage loss in the total kinetic energy of the spheres as a result of the collision. All right. So let's start by finding the initial kinetic energy. All right. So before collision, it was only sphere B that was moving with the speed u. So its kinetic energy is half mu squared. Let's also look at the final kinetic energy. That's after collision now. And after collision, we can see that particle A here was moving with the speed a. All right. So that's half mva squared plus the speed for particle B. Now the speed for B, it will be going in this direction, right? Okay, it will be going, the resultant speed will be going, say, in this direction, and the components are VB and U sine theta. So the speed is found using those two components, all right? VB and U sine theta. So the kinetic energy will be half m and the resultant of VB. So that's like the square root of VB squared and U sine theta squared. So that's how we find the kinetic energy of the particle B. All right. So this is essentially half m of VA squared plus half m of VB squared plus U squared sine squared theta, basically. All right. Now, it is important for us to understand, okay, because we need to know what VA and what VB is. All right. So according to what we have been given, okay, if you look here, we got that VA was U sine theta. So we know that VA is U sine theta. And we also been told that tan theta, okay, we actually got tan theta to be equal to 3/4. Tan theta to be 3/4, right? So if we are going to have this here, okay, this is a little right angle triangle, and this is theta, and tan theta is 3/4. It means this is 5 by Pythagoras theorem. So sine theta is 3/5. So VA technically is 3/5 and of U. All right. So this is what we have, and it's important. We can also find VB, okay? And VB, if we take any one of the equations from what we did earlier, let's consider this one here. Okay, let's consider this equation 1. So VB is U cos theta minus VA. Okay, U cos theta minus VA, basically. So U cos theta is 4/5, so it's 4/5 U minus 3/5 U, which basically is a fifth U. So we now know what VA and what VB is. Okay. So it therefore means that the final kinetic energy is half m of VA squared, this squared that is, which is 9/25 of U squared. And that's going to be plus half m of, for VB squared, that's going to be 1/25 U squared plus this, okay, sine squared is basically 3/5 squared, so that's 9/25. So we have 9/25 U squared essentially. All right, so we have right here, if I factor out half m, we have 9/25. Let me factor out half mu squared. So we have 9/25 plus 1/25 plus another 9/25. So that's 19/25 that we're getting here. So this will give us 19/50 mu squared. So that's the final kinetic energy in terms of m and u. So now to find, because the question was saying we should find the percentage loss. So the percentage loss in kinetic energy is going to be the initial kinetic energy, which we said was a half mu squared. So it's half mu squared minus the final 19/50 mu squared, and that's divided by the initial kinetic energy, okay, which is half mu squared, and we multiply that by 100 basically. All right, so this is like half minus 19/50 will give us 3/25, okay, mu squared, and that's over a half mu squared times 100. We know the mu squares will cancel, all right, and we will essentially be having 6/25 times 100, which would give us 24%. So this is the answer. That's the loss, the percentage loss in kinetic energy. So that's how we handle this particular type of question. That's how we do it.